Hello, my name is Daniel Salkeld, and this is my presentation for Lab 5. Introduction. So the purpose of this lab is to collect observational data of a magnet falling through a conductive tube of aluminum foil, and then model their interactions computationally, and then we compare computational predictions with actual observed data. Some key principles we'll use are Faraday's law, Biot-Savart law, Ohm's law, Lenz's law, magnetic force/flux, Newton's second law, and Newton's third law, and this will be more applied in the code as well. Some assumptions we have to make: there are no confounding variables like air resistance or other magnetic fields, so we need to neglect all outside confounding variables, and then everything was calculated and measured correctly. We have to assume that, and then that there was no other errors. Our main results is that the average time for our test was 1.298 seconds, and our code time was 1.29. So this is from the code. And then to the right you see Faraday's law, and then the Fg equals mg, which are key. Experiment. So the system is the aluminum foil tube and the bar magnet going through it. Surroundings are everything else. Essentially, we used a magnometer app to determine the end component of a bar magnet. Then we dropped that magnet through a conductive tube of aluminum foil 5 times, and then we took the average time it took to fall through. Then we calculated the same thing through glow script code using physics principles mentioned earlier. And some questions. What if we used a ferrous tube instead of a aluminum non-ferrous tube? Essentially, the tube's magnetic properties would have changed the behavior of the falling magnet, changing our observations. Then what happened to the magnet, especially in comparison to it falling in free space? So the magnet noticeably slows down as it falls through the tube, and in free space it would quickly fall because there'd be no forces acting on it. Some data. So our initial conditions are just the bar magnet and aluminum foil tube. So the foil is 0.3 meters long, had a width of 0.011 meters, inner radius 0.019, outer radius 0.030. Doesn't need to be 1 centimeter long. The magnet was 0.025 kilograms, and the magnetic dipole moment was 2.23. And I had to recalculate it using the magnometer app because my lab 3 had errors. And then the average time is the same ones as stated earlier. And then you can see the trials on the right. We had to do it 5 times. And here's the codes. As you can see to the left, we're defining the geometry of the tube and then the numerical patterns of the simulation, and then we're creating the actual tube and all its parameters. And then to the right, we're actually creating all the parameters of the bar magnet, and then we're stating our initial conditions and the formula to calculate the magnetic field. And at the bottom right, you see how we're calculating the flux through each ring due to the falling magnet. And then to the left is essentially also essentially controlling how fast the simulation runs. To the right is the gravitational force acting on the magnet, and you can also see us calculating the magnetic force on the magnet and the net force and all of that. And then here's the velocity versus time. As you can see, it's 1.29 seconds, so not too different. And then to the right you see the chart, and the flat part is essentially while it's in the tube how it slows down and has a constant velocity. Interpreting the simulation. So what do each of the colors mean? Essentially, the red is the north and it's counterclockwise, and then the blue is clockwise, and this is due to Lenz's law. So the direction of the induced current opposes a change in flux. And then what happens to the dynamics of the system when you flip the magnet around? The direction of the induced current swaps, but everything else doesn't change much. How does the total time in the tube of a real-world system compared to that of the computational system? How can the computational system be more accurate? So the computational system was 0.08 seconds quicker, and the computational system would be more accurate with formulas to account for external magnetic fields and other forms of resistance. And then what does the velocity versus time plot tell us about the force acting on the bar? So the flat portion essentially means that it's at a constant velocity, and the magnetic force and the force of gravity cancels out, and this is Newton's third law. And discussion and conclusion. So what if the resistivity of the conductor was reduced to 0, or as close as possible? How would it change? The current induced would increase drastically, making the magnet fall even slower. And then if there were holes in the tube, how would this affect the ring currents in your model? So the magnet would move quicker as the induced current would decrease, and the magnetic force will also be weaker, so it would just essentially fall through like it was in free space, or at least faster. And then any possible errors, any outside magnetic forces we didn't account for. I could have not set things up right, I could have measured it wrong, and the devices could have messed with the magnetic field readings. And there's my glow script code. Thank you.